Okay, Megan, give me a heads up as soon as we get YouTube. Hi, everybody in the room. Hey, everybody on Zoom, and presumably everybody on YouTube. Welcome to, yes, the next Water, Wetlands, and Watersheds seminar. It's February 4th, it's 2026, and we have our third speaker of the semester. We have Dr. Matias from the UF Department of Geography. So Corey Matias is a UF Foundation Research Professor in the Department of Geography here. When did you start at UF?
2005.
2005. That's when I started at UF too. But it's when I started my master's degree.
Oh,
Here, so yeah, somehow still here. I don't know.
Yeah.
They are a physical geographer who researches the spatial patterns of precipitation in tropical cyclones. They teach courses in climatology, hurricanes, atmospheric teleconnections, which maybe you'll tell us about today. Stuff happens over here and then stuff happens over there,
Yeah.
and they're correlated even though they're very far apart. They received the Class Teacher of the Year awards in 2009 and 2019, the Excellence in Teaching Award in 2019 from the Southeastern Division of the American Association of Geographers. And in 2025, they were selected as a fellow of the AAG. And the research you're going to present today was funded by NSF.
Yes.
So with that, Corey, the floor is yours.
Okay.
Thank you.
All right, well, so yeah, today's talk is going to be about moisture and hurricanes. And want to start off by acknowledging my co-authors. So Dr. Kim was a postdoc here with me and is the expert in the convolutional autoencoder. He received funding to finish this research when he became assistant professor at Soltech. And then my other co-authors, this was part of our Natural Science Foundation funding. We got to look at tropical cyclone moisture distributions. We'd already been working on a study that used a more statistical approximation, and I'll actually fold some of that into this talk as well. When we decided to go ahead and employ this convolutional autoencoder machine learning technique and kind of see what kind of different results we could get from that. So I'm mostly going to talk about the CAE paper, but I will fold in the more statistical paper as well. Okay, so let's jump in just a little bit here, because I know we're all scientists and we've heard of these things called hurricanes, living here in Florida. And so there's some important things to understand about how a tropical cyclone forms and how it's able to stay and keep its intensity, keep moving. So you can see that they are forming and moving over areas of warm ocean waters. So you're not seeing them sort of off the areas where there's cold ocean currents. You're also not seeing them along the equator because we need the Coriolis force, which is provided by the Earth's rotation. And so that would be at a 90-degree plane along the equator. And so you have opposite rotation in the southern and northern hemispheres. Now air does flow across the hemispheres, but a tropical cyclone would have to like unwind itself and wind itself back up so they don't cross over. So that's why you see that big gap there. And you can see then the Atlantic basin, we have a lot more systems that what we call become extratropical. They actually transition into cold core low systems by interacting with the colder, drier air in the middle and higher latitudes. And keep going out over the ocean to much higher latitudes than you might see in other ocean basins. And so it's kind of a unique feature of the Atlantic basin that we'll zoom out here. So you will hear me talk about extratropical transition. And so that would happen in these higher, more northern latitudes. Sea surface temperatures are cooler up here. There's a lot more wind going on, and they actually transition to become different systems. And so I did this drawing here as part of an art project to try to convey how tropical cyclones form and how energy is released within them. So there's two types of circulations, the primary and the secondary circulation. So the primary circulation is this rotational component. So there does have to be something called vorticity for a tropical cyclone to form, so you get that rotation either counterclockwise in the northern hemisphere or clockwise in the southern hemisphere. But then what helps to keep energy moving through the system is the secondary circulation, which is the in, up, and out. And so we can think about a tropical cyclone. They've got these really tall cumulonimbus clouds. They're producing really high rain rates. There's a lot of stratoformal clouds as well. There's a lot of moisture available, and it's producing so much rainfall. It's got to be able to replace that moisture fast enough in order to keep up with it. Because if we don't keep importing moisture in, and or we move into an area that's just too dry, you start to entrain that dry air and that stabilizes the storm. We need instability. We need these air parcels to be able to rise on their own so that they can condense, release latent heat, condense the moisture out, which then reinforces the lower pressure in the eye, which keeps the winds coming fast, which brings more in. So it's a positive feedback mechanism that we need to keep going. So we got to keep sourcing that moisture. So it's really important to understand where that moisture comes from, how much is available, and how it affects the tropical cyclones. So when we think about moisture advection, just in terms, so Kevin Trenberth is a very famous climate researcher that's done a lot on moisture distributions in different storm systems. So if we think about our tropical cyclone here as a collection of clouds, what we're thinking about is the faster the winds, the more evaporation that we can get. And so then we're evaporating, and the warmer the water, the more evaporation we can get. And so we need that to be highly efficient. We need to evaporate a lot of warm, moist water in order to uplift that and keep our clouds going. So what we do know as well is the tropical cyclone, there's sort of this rough estimate of a 500-kilometer radius from the center. So you'll see a lot of studies that say, okay, anything within 500 kilometers of rain that falls, that was the tropical cyclone. They do come in different sizes. They're bigger in the Pacific. They can be much smaller as well. So there have been hurricanes that fit within the eye of another hurricane. So there's actually quite a large range. But if we're just kind of scaling this just for conversational sake, so if we say that the circulation extends out about 500 kilometers, and then research is showing maybe about 4 times the radius of that, I mean, that would be 2,000 kilometers out, is how far it may be sourcing its moisture from. The study here said about 3 to 5 degrees away from the center, so that's maybe a smaller amount, but there's a lot of variation in tropical storm size as well. And so this study here, maybe only about 15% of the moisture that is needed can be sourced right under the storm, just not enough surface area to do it. So we've got to go from the outside. And so where it's coming from is this boundary layer, the lower 1 kilometers, the moisture that is evaporated and then advected up into the storm. So we're well away from the circulation for a lot of this moisture. Okay, so then some studies, particularly some modeling studies on tropical cyclones. And, is a dry environment always a bad thing? What happens to the outer rain bands? What happens to the interstorm circulation? And so it makes sense that where the rain bands run into drier air, you would reduce the precipitation there. So you could potentially expose the core to the drier air. So they do tend to be a little bit smaller in their circulation. However, we have found that, they may take longer to develop, but they can still reach the same intensity as in a moist environment. So if they're really efficient at using the moisture they have and they're able to stay small, then they can work with that smaller area and still intensify into strong hurricanes. There's something called the Saharan air layer, or the SAL. That's dry, dusty air that moves off the coast of Africa. It can reach us all the way over here in Florida. There's dust from the Sahara that they find in South America. So, that corridor, there's a lot of exchange of energy there. And so when we have this really intense Saharan air layer, so that's dry air, and so the mid-levels of the troposphere, it can intensify tropical cyclones in the beginning as you have that contrast, but if it wraps around and goes into the core of the storm, then it's going to weaken the system. And then we have something that we can add that's called vertical wind shear. So tropical cyclone, you want to think about this calm that you want to keep warm and moist so it keeps on going. So vertical wind shear would be when you have winds that are different directions and or speed with height. So in the middle latitudes, we have what's called a jet stream. There's really strong jet of air at the top of the troposphere. And then wind speeds are lower and lower as you get to the ground. In the tropics, you tend not to have that really strong flow up above. So a tropical cyclone needs to be without that. So you have really strong air blowing over the top. You can think about it sort of like breaking the cloud tops off and trying to push them over, push them away. So you tilt the tropical cyclone over and then it can't have a balanced circulation. So if it's strong enough and the shear is weak enough and it doesn't last that long, it can recover. But in some cases, it cannot. So vertical wind shear is one of the weakening factors of a storm. And so if you have that strong air that's sort of pushing here, and then you have dry air as well, then it's exposing, and that dry air is able to then come into more of the core of the storm and degrade the inner core, the radiance there. Okay, so let's get on to our study then of how we looked as an observational study at moisture distributions. So our data come from IV tracks. Is it publicly available, easy to get? You can get them as just like a CSV file, you can use them in the shape file, net CDF files. So it's a historic record of global tropical cyclone tracks. Most basins report every 6 hours, but they've interpolated it to a 3-hourly in the database. And so we're just taking the Atlantic Basin for our study. And because we were using precipitation rate from iMerge, which starts in 2000, that set our study area. And then, so this has the storm coordinates, this has the maximum sustained wind speed, a measure of storm size, the radius of tropical storm force winds, storm motion, what it's tagged, whether it's at landfall, and it's also tagged if it has completed an extratropical transition. We selected storms we call the mature TCs or hurricanes that had at the time of observation a max sustained wind of at least 33 meters per second or 74 miles per hour. In the Atlantic Basin, that's a 1-minute sustained wind speed. Other basins, it's a 10-minute sustained wind speed. So when you're comparing intensities across the globe, you have to think about, are we using the US system or are they using a local system there? So it's not always apples to apples. So when we put all these constraints, we ended up with 166 hurricanes. And then we got over 4,600 individual observations for our study. And so our other study did put limits on shear and whether it made landfall, but this study did not. We took everything as long as it was a hurricane and it was a tropical system, not extratropical at the time. Okay, so then where we got our environmental conditions, so what's considered sort of the state of the art right now is this 5th generation reanalysis of the European Center for Medium Range Weather Forecasts. You might have heard of the Euro model, watch the Weather Channel, that's these folks. And so they do have one of the most powerful forecast models, but they also have a very powerful reanalysis as well. And so they generate data that are hourly at a 1/4 of a degree lat long resolution, so it's a fairly high resolution. We did go and make sure that compared to the IV tracks locations, that it was representing the tropical storm, the hurricane center within 1 to 2 grid cells. Not all storms are well represented in the reanalysis, and that can cause some issues, so that's something you always got to check. The main variable that we looked at was total column water vapor, or you might hear me just say total precipitable water. And so what this is a measure in the whole column of the troposphere. If all of that moisture were to precipitate out, how tall would it be? How much would it be? Now, can all of it precipitate out at once? No. But again, it's giving us sort of the theoretical maximum possible. So that's what the measure is. And so you could argue, I mean, we know that most of the moisture is in the bottom layers of the troposphere. So if you've got sort of mid-level dryness versus low-level dryness, it's not going to show up necessarily equally. So that's something we do want to look at in the future, is looking at different levels of the troposphere where the moisture is. So this is just the whole column. We also looked at temperature distributions to look at the warm core, and we looked to calculate vertical wind shear using the zonal, that's your west to east, and your meridional, that's your north-south flow. And the standard calculation there is you go up at 200 millibars, that's where like your jet stream would be, and 850 millibars is about the top of the boundary layer, and that's also the layer where the tropical cyclone usually has its strongest rotation. So you would subtract the winds of those 2 layers. That's how you calculate your vertical wind shear. So you break it up into a westerly east-west component and a northerly or north-south component on that. We also looked at sea surface temperatures, and then this is the iMerge data. So this is integrated multi-satellite retrievals for global precipitation measurement. It's available at a 1/10 of a degree resolution, so we did have to do some regrading to get our data all on the same grid, which I'll explain about in a moment. So sorry, these are a couple of the boring slides. get out of the way, but I have lots of symmetry. Okay, so how did we deal with all these different data sets? So we used a natural neighbor interpolation. And we regridded the data to an 80 pixel by 80 pixel grid. And that's the grid that we needed to feed into the convolutional autoencoder. Now our domain, we went 1,000 kilometers out from the center on each side, and we need a square. So that's so 2,000 across and 2,000 up and down. So we got everything gridded onto that grid, and calculated our vertical wind shear, and calculated our warm core temperature. So we averaged the temperature data within 200 kilometers of the storm center. We also went within 200 kilometers of the storm center to look at what we call near core moisture, the area of 55 millimeters of precipitable water. And then these two metrics that Dr. Kim and I had used in a previous paper, rainfall strength, the mean rain rate within 200 kilometers of center, and then the rain area, all of the pixels that have at least a 1 millimeter an hour or higher rain rate from the iMerge data set. So those are all the variables that we went to look in. I won't talk specifically about all the results from that, we'll run out of time if I did. But those were just some different metrics that we came up with. Okay, so now on to Dr. Kim's specialty of the convolutional autoencoder. And so here is our input image, our 80 pixel by 80 pixel image. It's a flat image. And then there's processes that work on that identify the key features, and it keeps collapsing it down and collapsing it down and collapsing it down. And so eventually, as it's collapsing it down, we get to this flattened image that's 20 pixels. So this is the image then that we perform the cluster analysis on to determine how many patterns are existing. But then what you do to measure the success of it is then you decode it back to an 80 by 80, and then you can compare this image with the original image. And so some statistics on that. So the correlation between this image and this image was very high. And it's even better than the rainfall analysis we did, because sometimes rainfall pixels, you can have like a low rain rate right next to a really high one. And if you got too many of those, when you only have 20 pixels that condenses down to, it has to like make some decisions on that. But moisture in the atmosphere tends to be a little bit more predictable in its spread. So just like pressure would probably also do very well, moisture is going to do fairly well, temperature would probably do fairly well in this analysis. Precip is a whole other different mechanism there.
So the prediction and the input, the 80, each pixel has a value of precipitation.
For this, it's the precipitable water.
Okay.
So moisture. So moisture tends to be between 20 and 70 millimeters. That's the range that you're getting.
Mm-hmm.
And so just to understand the Rubin squared error, so that's a pretty good within 2 millimeters as an average. The sort of the worst image had about an 80% correlation. So they were all the images did fairly well. So this is an average over all the 46, 52 images. So correlation was high. It's getting the high moisture is being represented as where the high moisture is. And so we were very happy with that result. So here I'll just walk you through an example here. So the top is the original image that gets fed in, and then this is the reconstructed image. So it's a little bit smooth as it would need to be, as it was condensed down to a 20 and expanded back out. But you can see the major features are preserved. So this area of dry is still showing up as an area of dry. This little area of dry here is showing up fairly well. This is showing up fairly well here. This is showing up. It's maybe not quite as strong right here, but that general shape is still there. So it is picking up on these main features and these very sharp gradients that we're observing. And so that is what we want when we're trying to do this image comparison analysis. It's got to be able to condense them down into something that preserves the key features for analysis. Okay, so then, well, how many patterns of moisture are there? So this is where we get very subjective, right? We could pick lots of different combinations. And so the process that we used, so we made a graph here where we have the within cluster sum of squares. And then we have our number of clusters, and then we have this K-1 to K plot, and we use what's called the elbow method. So right here, there's sort of an elbow, right here, there's a little bit of an elbow, and right here at 6, there's a little bit of an elbow, and everywhere else it sort of passes straight through. And so that gave us the first clues on where we should look. Obviously, too many clusters, we're not doing our job as modelers of simplifying reality, but too few, we might be missing something important. So, and we went through all of our spatial plots, temporal plots, so I'm not going to show all those here, but I'll show. So these are the spatial patterns if you just had 2 clusters. Here's your 2 cluster solution. You can see the n is a lot higher in this pattern. So that might suggest there's something else going on here, but you can see that basically we've got something that's not as strong of a gradient and something that is a very strong gradient. And then as we split, so these 2 look very similar, but this sort of seems to be a third pattern that emerges if you go to 3 clusters. And so you can see that there's some a stronger asymmetry in the sort of northwest to southeast direction. And the literature talks about that, especially with the Saharan air layer. So that definitely seems valid. When we go to a 4 cluster solution, we can kind of see similarities here, similarities here. And it kind of looks like what we're doing is we're getting a more moist and symmetrical sample versus one where it's a lot more compacted. It's really moist in the center, but then it dries out, but not to a huge amount of dryness. But it seems like maybe a combination of some of these are popping that 4th one out. So we ended up going with a 4 cluster solution. You can see as we go down to number 6, we can see again, there's similarities to what's going on upstream. So it's what is it breaking out? Is that an important feature? And that's something that spatial mapping actually helped us with as well. So again, subjective. Okay, so here is our 4 cluster solution. And what we named these clusters is our cluster 1 here that had the highest N. We call this moderate moisture and symmetrical. So it does have a very symmetrical shape. It doesn't get super dry. So there isn't really a sharp gradient, but the highest moisture in the center is fairly compacted down. Versus here where we also have a lot of symmetry, but moisture is much higher farther from the center. So we call this high moisture symmetrical. And then these bottom 2 were our more asymmetrical distributions where we had less moisture to the northwest and more moisture, especially here to the southeast, which is better for the storm. So we can see here we have a very small core of moisture. And we can see the colors aren't as dark in here. So even the core of the storm doesn't have as much moisture in this cluster. Versus here, there's actually a lot of moisture in the core. So there's a sharper gradient here till we get this drier air to the northwest. And so just a couple of our metrics here as we kind of show the distribution of those. So we can definitely tell that this 3rd cluster here, there's a large range of moisture. So some are actually fairly dry in that near core of the inner 200 kilometers. And then the area of the 55, which is our dashed, we can see that these two have much larger areas compared to these 2, which have much smaller areas. So it's interesting is this has a decent amount of near core moisture, but the area of the 55 millimeter is actually fairly small. And so this helps us to understand that, okay, these 4 might be pretty good choices. We're seeing some differences here in the configurations. Okay, so let's map these and let's talk about when they might be forming during the tropical cyclone season. So the Atlantic Basin season starts June 1st and ends November 30th. There have been activity in May and December, but that's the majority of the months here. And then we look at our spatial patterns. So this is the one that's a weak gradient, but it's all compacted into the core. This is happening kind of out in the middle of the Atlantic. And it's one that's a little bit more in the early season. You don't see this as much in the late season. This is our high moisture, symmetrical, biggest rain rate area. And you can see this is most of the Caribbean. Although not the West Gulf, which is interesting. This is the only one that has anything on the West Gulf. And so again, you can see that that's sort of a little bit more early in the season. Then this really stands out. These are all far to the north. So as we'll see, these are ones that are going to potentially extratropically transition. So SSTs are colder up here, vertical wind shear is higher up here, your warm core is smaller up here. And so it makes sense that these spatially clustered where there's a lot of drier air all the way around. And then this was an interesting one because this would be like where it becomes a hurricane fairly early, as the wave is coming off of Africa. And then these could be storms that are a little bit older that are about to make landfall. And this is the only one that's got the West Gulf. And so one of the things we're thinking about is maybe Saharan air layer here is looking similar to the dry air that you just get off the continent as you're moving to the West Gulf. There's enough spatial similarity there that these are joining into one cluster. We did keep going to 5, 6, 7 clusters. This did not break apart. So that was something interesting we put in our supplementary materials on that. Okay, so some of the attributes then of the different clusters. So when we look at storm intensity, we can see that that further north cluster is a lot weaker. So they are all hurricanes at the time of analysis, but you can see that the average intensity is much lower. So again, 33 meters per second is our cutoff here. All of them were at least 33 meters per second. And so not surprising where there's more moisture, a lot of these were a lot more intense. Storm size, these are actually the biggest ones. And that does make sense as they start to recurve and interact with the westerlies, they start to kind of spread out in their outer wind radius. So even though the core is weakening, the outer wind radius is spreading. This is something that in Canada they have to look out for with their landfalls that they get there, because the storms are growing in size, even though the core is weakening as they make landfall there. And then our rainfall metrics, what's interesting is the rain area is actually smallest in this cluster here. And this is the one with the weak gradient that was really compacted. So it wasn't super dry on the outside, but it was just so compacted with the higher moisture. And so we can see then these are the rain rates then from the iMerge data. And then we've also overlain on top of that our storm motion in the purple arrow. So most of them are moving towards the northwest, except for these extratropical transitioning ones. What happens is this tropical cyclone comes across and then it starts to turn more to the north. And if it keeps going, it races off to the northeast. So this makes sense. These are ones that are about to start to transition to become an extratropical cyclone. So they're moving fast into the northeast at the time. And then this is the vertical wind shear. And so that also makes sense. They were having higher vertical wind shear because of the stronger upper level winds as it moves farther north. The vertical wind shear is a little bit weaker in these other systems. And so you can see that we have a much more asymmetrical rainfall distribution here and a lot lighter rain rates. And that's not surprising. Again, this is the one that was surrounded by a lot more moisture. So this is the one that had the weak gradient. You can see the rain rates in the core are still fairly high. They're just not really spread out. This is the one with lots of moisture all the way around. So not surprising. There's really high rain rates with that particular composite. And then just to look at some of the environmental conditions. So these would be the sea surface temperatures. So the warmest waters here in the Caribbean, that's not surprising for that particular cluster there. The coldest waters would be for the farther north. So that's not surprising either. There's not a huge difference between these. So that was the middle of the Atlantic, and that's the one that's far east, far west. This is our warm core. So again, the warm core is really disappearing in these cases that are starting to transition to extratropical. It's very strong here where there was the high moisture. And then vertical wind shear. So the length of the arrow is giving us an indication of the fastness of the winds, as well as the coloring as well. And so you can see there's a little bit of shear around all of them. But here, this is where we get these reds, and it's actually coming within the circulation of the tropical cyclone and starting to affect the core. So that's where the vertical wind shear is very, very high. And then what's helping this asymmetry in this particular cluster is, again, there's strong shear, but it's only to the north, and it's not quite getting into the core of the storm yet. And so we can see very different, especially again, for this one that was dry all the way around, a very different environmental profile. So again, that leads high confidence that these patterns may be a consistent feature, not just something that like the computer randomly generated. And then just some stats on how likely it is for each cluster to be the first time it was a hurricane or the last time it was a hurricane. So not surprisingly, the last time it was a hurricane, most of them were in that far north cluster. So that's your exit cluster. A very common transition would have been to go from cluster 1 in the middle of the Atlantic to cluster 3. The other pathway that was popular would be to start as cluster 2. That was the Caribbean one, and then end up going more into the West Gulf and making landfall in Mexico or on the Southeast US. So those were two common pathways there. So you can see that quite a few of the hurricanes did extratropically transition when that were a member of that cluster 3. And then the highest landfalls, so the Caribbean, a lot of these are small islands, so maybe not as many people involved, whereas these are Mexico and the United States, so larger land masses, so they did end up dissipating a lot of times after landfall. We're here in the Caribbean, if you're passing over a small island, you get a little bit of disruption, but if you go back over the water, you can ramp back up afterwards. So a lot of these kind of kept on going. Okay, so now let's talk about what we found in our companion paper.
So you got about 20 minutes total before.
Okay,
Yeah.
okay, we're in good times here. Okay, I didn't go like too far. Okay, so the lead author here was one of the master's students that was on our project, so this was part of her thesis. And then we also have the one of the other master's student that was originally at Mississippi State, and then Dr. Wood moved to the U of A. But that's Catherine, so Kaylee and Catherine. So they were the students on this publication. And so we had been working on this already when we started the convolutional autoencoder part of the analysis. So we had already decided, because we're using the iMerge data, that this would be our study period, that we're just doing Atlantic Basin hurricanes, and they did have to be hurricanes at the time of analysis. And we're getting that moisture data and all of our environmental conditions from ERA5. So those were the similarities, but differences. So in this study, we wanted to restrict vertical wind shear. So these are what we would consider low shear cases. So you're not going to see those far north cases in this study. Vertical wind shear was as high as 20 meters per second, so twice the amount here. So these were lower shear cases because we know shear destroys the circulation. So we wanted to kind of control a little bit for shear so that moisture would be a more dominant mechanism instead of always being dominated by shear. We also wanted them at least 100 kilometers away from major land masses. So, moving over a very small island didn't exclude it from the study, but a landmass like Cuba, for example, is large enough that if it moved over Cuba, we excluded that from the study. We also put a constraint that it had to stay a hurricane for at least 24 hours, so that these were not just kind of like blip up, blip out, but they were longer lasting hurricanes. And because we were going to do an EOF analysis and pure orthogonal function, we needed to have an absence of spatial temporal autocorrelation as much as we could control. So obviously the previous analysis where we're putting in data like every hour, they're going to be highly related one after another, which is fine because that's an unsupervised classification and you need to feed it as much data as possible. It doesn't bias it. But in the statistical analysis, we could be very biased from a very long lasting storm. And so we said that the samples, if they were from the same storm, had to be at least 48 hours apart. And so doing this empirical orthogonal function analysis, basically what we're doing is we're looking at the patterns, and it's kind of like drawing a regression line through the spatial patterns. And you're trying to see the best fit line that you can draw through the first pass. And then you go 90 degrees and you draw another best fit line, and you go 90 degrees, and you draw another best fit line. And so you can draw as many lines as you have variables to look at, but then you're not really modeling, you're not really explaining a lot. So there's different ways to figure out how many of those lines you should keep in the analysis. But our first two lines, functions 1 and 2, explain 55% of the variance. And so we went with that, which if you loaded onto it positive or negative, that gave us 4 profiles. If you go to a third best fit line, you get only 8% explained variance added. So not a lot of value added to go to number 3, although we are looking at number 3 in another paper that we're currently working on. The other difference is we excluded the storm center. So we excluded that inner 200 kilometers. Does it make a huge difference? Probably not, because that's a small area of this whole area for the spatial pattern. And also in most of the samples, that was fairly moist anyway. So it probably didn't change a whole lot to exclude that area, but we tried that for this. And then we put an additional restriction, because we checked each case, we checked the loadings onto each function, and we said we would only take one storm loading onto a component. So if there was multiple loadings of the same storm onto a component, we only took the strongest loading. So this reduces us down from what we looked at from the other study to only 75 cases from 61 hurricanes, instead of over 4,600 hourly snapshots from 166 hurricanes. So this is a much smaller sample. And here we're doing a radius out from the center, so we actually have a circular domain instead of a square domain. So that for other study would have had data kind of out on these little edges that went into the image analysis. So we might have lost just a little bit of information here by comparison as well. And this is just a sample from Hurricane Alberto in 2000, just so that you can get a sense of the distribution of moisture here and what it looks like without that really strong core like we saw on the other. So here we can definitely see there's really dry air again to the northwest, but also interestingly, there's some dry air to the southeast too, which the equatorial side tends to be more moist. So that's sort of an interesting case that could be embedded in the Saharan air layer. Okay, so I flopped these a little bit so that they would match up side by side. So what we have is a match here between what Addington is calling moist southeast and our high moist symmetrical. So these are the Caribbean ones. These are the ones with lots of moisture all the way around. So this is what on ours was cluster 2. And so we can see here again, there's a lot of similarities. It's a little bit drier up here, but a large ring of moisture and moisture to the south as well. Then our next pattern, what they call dry extreme, there were 13 cases that loaded onto that component, and that matches fairly well spatially with our low most asymmetrical. Now, these have a lot of those high wind shear cases. Those were excluded from the study. So there we'll see the difference in the table based on that one. Then here, they're a composite of what they're calling dry southeast. Looks a lot like this composite here, which was our cluster 1 that was up in this corner, that has the really compact but not super dry on the outside. And then our asymmetrical one is in the same order here, where we have drier to the northwest and moist to the southeast. They also have one that they're calling dry northwest. So we see that very similar spatial pattern there. And so what we did was we took their 75 cases and we looked at our larger analysis and to see which groups everything fell in. And 3 out of the 4 groups had very strong agreement. So the only one, so our low moisture asymmetrical was full of those strong vertical wind shear cases, and they excluded those. And so some of their dry extreme loaded onto the moisture asymmetrical one. So that one instead of that one. So that is the only one that didn't match up quite as well, but the other 3 were very strong match. So that gives us even more confidence that our convolutional autoencoder and our 4 cluster solution are revealing physically relevant patterns in the atmosphere. That it wasn't just some sort of accident of how the computer analyzed the data. That with a different type of statistical analysis, we're getting these similar patterns. Okay, so then just kind of going back to summarize those patterns. So our first group was the moist, moderate, and symmetrical. So these tend to be a really weak gradient, really compact though. The moisture is still high in the middle, so you've got high rain rates near the core of the storm, but not a lot of rainfall area outside of that. These were a little bit more early season, and these were out in the middle of the Atlantic, so they weren't too close to land. Not a lot of them made landfall, but it was fairly popular to start out in this particular cluster first becoming a hurricane, because it's out in the middle of the Atlantic where they might develop. The second pattern then that came out was what we called high moisture symmetrical. Very little dry air, all the way up to 1,000 kilometers on any side. High moisture spread far, really high rain rates in the center. These became the most intense storms. There's a lot of energetics available to them. They were mostly in the Caribbean, especially off Cuba. These made the most landfalls because of their motion through the Caribbean as well, and a lot of them kept going after landfall and stayed hurricanes. So you made landfall, but you didn't just dissipate, you kept going and potentially made a second landfall. So these were over areas of the highest waters, which makes sense. You would have a lot of environmental moisture over the warm water. They had the warmest core, they were in very low vertical wind shear, and they produced the heaviest rainfall. So in terms of like danger, these are really, really dangerous. They've got all this moisture feeding them and they keep going. Then we have our northern group, the areas of low sea surface temperature and high wind shear towards the north of the Atlantic. So these are a lot of the recurving hurricanes. So it's very dry all the way around the edges. But they were the weakest intensity, but they were the largest size because they're spreading out in their circulation as they're moving farther north. These were happening more later in the season, highest vertical wind shear, the lowest rain rates because they had the least moisture and they were undergoing these transitions. They were moving the fastest and most likely to become extratropical, to fully restructure into what we call the cold core low system that's powered by the jet stream and cold air contrast. Rather, a tropical cyclone is powered from the bottom up. It's powered by evaporating this warm moisture, these warm waters, releasing that latent heat, keeping that engine going is bottom up. So it transitions in these cases to a top-down power. And then our fourth group, which was kind of the interesting group, was the most asymmetrical. We had really dry to the northwest, but really moist to the southeast. And so this actually had the highest moisture right in the center. And it had the larger rain area associated with it. And it had that funky east-west split. So there was some in the East Atlantic, and then in the far west, it's the only one that was in the West Gulf. Again, as a hurricane. So these were all hurricanes at the time of the analysis. So vertical wind shear was moderate, but it was still surviving that. And then this had a really high number of landfalls, and then it tended to stop being a hurricane after landfall because you're moving over a large landmass like Mexico, the United States. This was very often you ended as this group or you ended as this group. So either over land in the deeper tropics or out over the ocean over these non-favorable conditions to be a hurricane, and the most popular of the 10. And then, so yes, our companion study with a different statistical technique and a smaller sampling and a more strict sampling, but we still found these 4 components or 4 clusters that had very similar patterns. And so that gives us reason to think that these may be, realistic patterns. And some of our future work, like I was saying earlier, what we'd like to do is look at different levels of the atmosphere. Is it the Saharan air layer? That's something that's happening at a very specific level. So if we looked at 700 millibar moisture, that might be the smoking gun for Saharan air layer versus moving over like a dry continent like Mexico or, where Texas comes, that dry air mass that's sitting over North America, that's going to be drier over a larger number of altitudes. So we could test that if we could slice the atmosphere into different levels. So that might help break that cluster for a little bit. And then just to kind of close, so I wanted to show this sculpture that I created because I'm also a sculptor and I like to put weather into my artwork. And I got to be part of this show that was at Hillsborough Community College down in their Ybor City campus. And the show was about loss and resilience in community in case of flood. And the idea from the show came from last year, especially Hurricane Milton and the damage it did in the Tampa area. Of course, several hurricanes did a lot of coastal damage, but Milton actually came inland and did a lot of damage as well. And so your artwork had to use some sort of relief supplies. So I said, okay, water bottles, that works for me. And so I welded up this frame. And then what I did was the water bottles are losing water, not in real time, but they're just filled at different levels because that make a mess. It wouldn't last very long. But so they're completely full as they're coming into the circulation, and then as they move up, there's less and less water, and then the top ones are empty. So it's trying to show that the water is sort of, you know, being released into the atmosphere. And then I wrapped these full ones in maps of rain rates for Florida hurricanes. And it was meant to be that people could take them, but people are shy, and so they didn't take them. So they were there at the end. Like I had a whole nother backup tub of these. But the great thing was, so we didn't get it. So part of the show was you had to agree, if another hurricane came, they would take your stuff and distribute it to the community. So your sculpture's gone. You had to be okay with that. I was like, that's fine, that would be awesome. Well, one didn't come through Florida, but somebody was able to get on a relief flight to Jamaica. So I got a message that my labeled water bottles were on a flight to Jamaica.
Okay.
Now, if I'd have known that, I would have put rainfall from Jamaican storms.
Yeah.
So it's all the Florida storms, but, so this is like my idea got to actually put people in Jamaica, so it's like really, really cool. So I was really happy to be a part of that, so that's where this little drawing of the eye wall kind of came, so I'm trying to sort of educate the public as well as think about something sort of artistic and three-dimensional and in a different way than taking on the information. But yeah, just wanted to put a plug in there for art and science, that these actually go together very well. That's something that I'm integrating into my career, so.
Nice.
Okay.
Thank you for it. All right, we have 2 minutes for questions. So anyone on YouTube, please drop your questions into the chat. We got a comment already, very cool sculpture concept from MM Moffat, whoever that is. Thank you very much, MM. All right, in the room, any questions for Dr. Machas? Yeah, sure, Yash.
So do you think that in the future meteorologists or like the National Hurricane Center could use the clustering to kind of better predict the storm intensity? Like if they know what it looks like at the initial points and kind of predict where we go?
Yeah, so that's, and there's more in our paper that I didn't have time for, but we actually looked at like the next 36 to 48 hours. Ones that were intensifying versus de-intensifying, what characteristics did they have? So there's some kind of predictive quality based on where it is now. And so, yeah, definitely. Our earlier study that did the convolutional autoencoder, but with the iMerge rain rates without all the moisture data, we actually got to present that to Jacksonville National Weather Service office. Holds a symposium, and they invited UF researchers to be part of it. And so we actually got to present that work. And the one cluster, they don't quite line up, so you're not going to know what I'm talking about. But the one cluster that showed the rainfall coming off the west coast and into Florida, they're like, we recognize that cluster. Like, we see that when we're actually forecasting here. And I'm like, yes. So I have a forecaster saying that our clusters are something they recognize. So it's happening. So these methods are seeming, these pattern recognition methods are revealing realistic features of the atmosphere that we use when forecasting.
Yeah, Nick.
So I saw the slide, and you might have talked about this with the spatial distribution of the clusters. And just each one of those grid cells for the full, we've shown how frequently they occur over time. Yeah, this,
Sorry.
the next one,
There we go.
have you guys tracked the temporal evolution between the four clusters, and if it tends to look similar, you know, throughout the initiation phase of a hurricane, and then when it eventually dissipates?
Well, so we didn't start by like the first time it ever appeared, so only from when it first became a hurricane to when it left a hurricane. But we do have maps that show the whole track, not just sort of this by cluster, but they're really hard to read because it looks like a spaghetti, a spaghetti map. So we did sort of have like an average of all the actual tracks within each cluster as well. But that's when we also looked at sort of the time in each cluster and how common it was to cross from one cluster to the next cluster. And that's where we get the fact that so it makes sense that this is most popular to be ending in this configuration. And then so there was some that start here, and that makes sense. This is actually like the farthest east that you could be a hurricane. But actually, this is the one that was most popular to first become a hurricane in. So these would be if you have a really strong subtropical high pressure system sitting out here and the winds are kind of coming like this, they're going to steer the forming clusters, and they may not form back out over like the Cape Verde Islands. Sometimes the tropical waves take a while. They move across before they can form. Sometimes they actually move all the way across here and don't form until the East Pacific. But the original vorticity cluster that you can follow on the satellite image came all the way from Africa. So sometimes they just don't develop until they go, or they don't develop at all. We get about 80 on average, like easterly waves. And so you can see maybe, 5 to 10 develop into a tropical system, not even a hurricane. But what is it, the statistic about 70 to 80% of major hurricanes form that way. So that if they can stay in this zone here of really warm water, low wind shear, unless it's an El Nino year, El Nino makes a lot of wind shear through here. But La Nina or neutral, you get relaxed winds here, you got the warm water, which means a lot of moisture is available. And there's just not a lot in its way. There's no land that it runs into. And it's hard for a trough to dig all the way down to this latitude in the main part of the season. So if they're able to form and move along this track, they become a hurricane, and then they can stay a hurricane all throughout here. And so that's where they can grow, they can intensify, they just keep feeding into that moisture. And we also have a gyre that sits down here and basically like pumps some vorticity and pumps moisture all into this Caribbean region as well. The Central American gyre. So that's more recent research, like in 2015, that started coming out in the literature as a feature that had been understudied in the past. So there's several things that are kind of going on to make this region like sort of, I would say, the hotbed, but the hotbed for this kind of storm. So if it first becomes a hurricane in here, it has a good chance of keeping going. This is an area also, though, depending on, there's something called the tropical upper tropospheric trough, or the TUT. And early in the season, it tends to sit out in this area and it puts a lot of wind shear in the upper levels. So that can be a destructive thing. So if a wave comes here and the TUT's strong, it won't develop. But if it's strong enough and the TUT is just at the right strength, it can actually feed off of it. It can give it enough energy, it can give it a little lift, and then spur it to develop as it moves past that. So there's a weird sort of zone here where it's like, will it or won't it? And it depends on the scale of that interaction. So that can kind of make forecasting a little bit tricky in the area.
Yeah, we'll have to stop there, but let's give another round of applause to Dr. Monaco. Thank you so much. Really appreciate it, and we look forward to another year of no landfalling hurricanes or tropical cyclones or storms in Florida. Next week our speaker is Ray Goldsby, and Ray's going to talk about using wetlands in the fight against PFAS pollution. So that should be a really good one. He's coming, he'll be here live. Maybe a chance to join us for lunch after if you're studying this and you want to talk to Ray a little bit more. Until then, we'll see you all next week. Thank you very much.